What up, calculus students? Let's do the lesson 4 homework. We understand the slopes of secant are secant x times tangent x. We know constants stick around. We're just finding the slope of the tangent, so we need the slope equation at the value. Guess what? You need to know how to find the secant of pi over 3. Secant of pi over 3 is the reciprocal of the cosine of pi over 3. Cosine of pi over 3 is a half. So I get 2. Now, how do I know that? Not because I memorized it. I thought of my pi over 3 triangle. I remember the short side is the cosine here. The tangent of pi over 3 is the opposite over the adjacent of my pi over 3. So that's a root 3 over 2 divided by a half, which is a root 3. So I have 4 times 2 times root 3. This is cricket out. Eight root 3 is my slope of the secant function. Giving you this tangent over 8, not so that you have to use the quotient rule, so that you realize you don't have to use the quotient rule. You can write it 8 times tan x, which means the slopes constants stick around unless they are by themselves. So that 1/8 just sticks around. Don't have to use the quotient rule. You get 1/8 secant squared x. If you plugged in pi over 3, the secant of pi over 3 is the reciprocal of the cosine of pi over 3. We already talked about the cosine of pi over 3 is a half, so 1 over a half is 2. But secant squared is really the secant of the value squared. This is very important to know, that notation, which a lot of students forget, that secant squared is really the secant of x squared. So I have 1/8 times 2 squared, or 1/4, or sorry, 4/8 or 1/2. Cool. Cosecant slopes are negative cosecant cotangent. These are just things you have to remember. From your notes, we talked about sine, cosine, sine going with cosine, tangent going with cotangent, and secant going with cosecant, secant tangent. Have this written down. This is one of those things that we have to memorize and figure out a way to do it yourself. All right, so pi over 3. I need the cosecant of pi over 3 and the cotangent of pi over 3. So I'm still on my pi over 3 triangle. Cosecant is the reciprocal of sine. So the sine of pi over 3 is root 3 over 2, which means the cosecant is 2 over root 3. The cotangent would be 1/2 divided by root 3 over 2, which is 1 over root 3. Look at how this works out. If I multiply these together, I'll get negative 6 over root 3 squared, or negative 6 over 3, which is negative 2. Pretty fascinating. I'm going to graph this equation of the tangent line just because I like doing it. Here's the cosecant function. We found the cosecant of pi over 3 is 2 over root 3. And the slope was negative 2. Oh, that's not right. What did I make a mistake on? Cosecant of pi over 3 is the reciprocal of sine, so that's 2 over root 3. Cotangent is adjacent over opposite. So that's a half divided by root 3 over 2, which is 1 over root 3. I get the negative 3 times the 2, which is negative 6 over 3. I feel like I'm taking crazy pills. It's been a weird week, man. I'm just gonna throw that out there. It's been a weird week. Some of you guys are just like doing less, and I'm starting to get frustrated more. And now it's like, what the hell? I can't even do this homework problem. Negative cosecant cotangent. Cosecant pi over 3. That's correct. Cotangent of pi over 3 is correct. Oh, gosh, I know what I did. I didn't multiply the 2 over root 3 by 3. So I was right. What? The cosecant of pi over 3 is 2 over root 3 times 3. What is going on? Gosh, I'm really sorry. You know, it's like you do it over and over again and you just miss out on things. I forgot to put the 3 in front of cosecant x. I also forgot, like, yeah, I screwed up a bunch of stuff. But now we're correct. Look at that. Hooray. There's that tangent line. Cool, Mr. Messenger. That wasted a lot of time. Now let's use the product rule. Slopes of the first times the second. So why am I using the product rule? X's times x's. X over 3 is the same as 1/3 times x. The slopes of x over 3 is 1/3. So slopes of the first times the second plus the slopes of the second. This is not going to be fun. Which is negative cosecant cotangent times the first. Woo! This is going to be gross. But that's okay. I'm going to plug in pi over 6. Okay, pi over 6 triangle. The cosecant is a half. It's going to be the reciprocal of the sine. So the sine of pi over 6 is a half. Cosecant is 2. The cotangent is root 3. Pi over 6 divided by 3 is the same as pi over 6 times a third. So my slope is 2/3 plus negative 2 times root 3 times pi over 18, or I can simplify the 2 and the 18. My slope is 2/3 minus root 3 pi over 9. Watch. We'll just make it easier on ourselves. F of x is x over 3 cosecant x. Yeah. I probably said the same thing in the homework video. I'm like, oh, this question stinks. F of pi over 6 is that value. So I'm going to plot the value pi over 6, f of pi over 6. There it is. And I will have y minus f of pi over 6 equals the slope that I found was 2/3 minus square root of 3 pi over 9 x minus pi over 6. Look at that. Sick. You know, sometimes you got a bad problem. Things are looking down. We feel pissed. But then, like the next problem, you just crush. you feel really good about yourself. Cool. Done with all of those. Let's move on to some notational derivatives. Don't forget, the slopes of g are just the slopes of g. The slopes of f are just the slopes of f. If we need to use rules, we will, but I don't need to here. Slope of g at 1 is given to us, the slope of f at 1. But what if you have a product? Again, this is like a notational derivative, just keeping you ready to use your rules. Slopes of g times f plus the slopes of f times g. That's the slopes of the first times the second, plus the slopes of the second times the first. Plugging in 1. G slope at 1 times f at 1. That's the y-coordinate. F slope at 1 times g of 1. Okay. Checked out. G slope at 1 is 4, f of 1 is 3, f slope at 1 is 5, g of 1 is 2. 12 plus 10 is 22. You're going to see a question like this on your test. Guaranteed. And it's a question making sure you remember what started as an average rate of change formula and turned into an instantaneous rate of change formula with the addition of the h approaches 0. Hold up.
I'm trying to figure this out. I can't factor that.
Okay. Your slopes need to equal your slope.
Yeah,
So this is that's the idea behind things being parallel. Slopes equal slopes.
I know, but I'm trying to solve for y so I can write the equation. Or not y, x.
Why?
So that I can get the x to write the equation.
Why? You have the slope of the line.
Yeah.
What's the slope of the line?
Isn't it 9? Right? Or 1 over 9?
Yeah.
Yeah.
How do you find the slopes of x over x minus 1?
I know you do the quotient rule to find the tangent line, and then you set it equal to 1 over 9.
Yeah.
Or negative 1 over 9.
I feel like you didn't take the equation. I didn't think you found the slopes.
I haven't done the slope yet because I still need to solve for the x, no? Or do I solve for the x?
Why?
So that I can write the y minus y1 equals mx minus x1.
Let's find the x location by taking the slopes of the function and setting it equal to that negative 1/9. And that's how we'll find where x is. Cool? I feel like you're going on a path that might lead you in the right location, but you still need to just find x. And where you're going to find x is your slopes equal your slopes. All right, cool. So remember, like average rate of change was like a y2 minus a y1 over an x2 minus an x1, which was just a distance of h. When we attach a limit to that, it becomes an instantaneous rate of change. Okay, so this is actually asking you for the instantaneous rate of change of the secant function, like the secant function. It's asking you for the slope equation of secant. The answer is just this. This does not involve actually doing anything like plugging in 0 or doing anything limit-wise. This is actually a question where you translate what you see into they're just saying if f is secant, what are the slopes of secant? This is the slopes of secant, secant x tangent x. This is very similar but only we see like pi over 4, x is approaching pi over 4. Well, that looks like a y2 minus a y1 over an x2 minus an x1. But it looks like we're looking at pi over 4. This question is asking us, and this is how we handle this. We translate this to what is the slope of tangent x at x equals pi over 4. So f is tangent. The slopes of tangent are given to you by secant squared. We need to find the slope of tangent at pi over 4. So I need to find the secant squared of pi over 4. Cosine of pi over 4 is root 2 over 2, which is 2 over root 2, which I square, which is 4 over 2, which is 2. Do it yourself. Make sure you can get it. All right, moving into higher order derivatives. If I ask for the 52nd derivative of cosine, you might feel intimidated, but you have to realize that things will start repeating themselves after a certain amount of derivatives. Every fourth derivative, we're back to cosine, which means the 8th derivative is cosine. The 12th derivative is cosine. The 48th derivative is cosine. The 52nd derivative is cosine. Cool. Notation, this is the third derivative, but we already have the first derivative, which means we just have to find the slopes 2 more times. Slopes of the first times the second, plus the slopes of the second times the first. Now, slopes of sine or cosine, cool. But look at what happens when I have to take the slopes of cos x times x. I have to use the product. Slopes of cosine is the slopes of the first times the second, plus the slopes of the second times the first. What do we realize is, and you can simplify, we have 2 cosine x's minus x sine x. Did you get it?
I know what the x's can be. So
Good.
do I plug in x to find y?
Yep. Into the original equation.
Okay.
And then you'll have your equations, your tangent lines, because you know both of the slopes have to be negative 1/9.
My location was negative 1/9 too.
No. I feel like the answers are like 1 and 4 or something like that.
No, because if I plug in 2, one of them is 3/9 and one of them is negative 1/9.
Oh, you're saying the x's are 2 and negative 4. And if you plug in 4, you get 4/3. If you plug in 2, you get 2.
What? How?
Or you solved this and you got your x locations are at negative 4 and 2.
Oh,
Plug it back into the
yeah, plug
original
it into
equation,
that
negative 1.
equation.
Yeah. Oh, well, if you plug it into the other equation, you're going to get negative 1/9
Yeah.
both times because you found that at this x you have a slope of negative 1/9. All right, so pay attention to the fact that you already have the first derivative. So when you take the derivative, you already are at the second. Take the derivative again, you're already at the third. Take the derivative again, you are at the fourth. This one's interesting because we will realize that this one's going to go away, but this one will not. Now, since I need to go to the third derivative, I'm not going to rewrite this because I'm just going to have to rewrite it again. I will get here, and then I will end up with 0 here, but negative 6x to the negative fourth there. It's just an interesting thing where it's like if you start with any other power besides a positive whole number power, like starting with a negative power or a fractional power, you will have to continue to take derivatives over and over. Okay, We talked about being differentiable. It means you have a tangent slope. To be differentiable, you must be continuous. You must have no sharp points. Cool? So we have evaluated the function's continuity. We would look at x equals 2, and we'd make sure that 2 to the right and to the left would give us the same value. 4 equals 4. Correct. However, now we are going to look at the slopes of our pieces. And we have to make sure that there are no sharp points, which means the slopes of our pieces meet up in such a way that it's nice and smooth. So we will also look at the slopes to the left and the slopes to the right of 2. Because 2 is the important value, we realize that the slopes are also equal to 4, which is the same as the function value. So we would say this piecewise function is differentiable everywhere. Let's look at this guy. I have the function and I have its slopes. Cool. I can see that the slopes, and again, it's not always 2, but in this case it is, are going to be 12 equals 12. Your slopes do meet up. However, watch what happens. The function is not continuous. Since the function is not continuous, oh wait, it is. It is. So yes, it's continuous everywhere. Not good examples. Should have had one that's not. I mean, I could have changed one thing. If I change this from a 4 to a 5, just like a heads up. If this was changed to a 5, then it would be, oh, wait. No, stop. I messed up. It's not. I screwed up. If I go 2 to the right and I plug in 2 is 24, 23, 22, 21, 20, that's 20. This is not true. 8 is not equal to 20, which is a no. So we are not differentiable at x equals 2 because we are not continuous. Cool? So that's the thing. We have been used to just checking f, but now we also have to check f slopes of our pieces. Remember, a and b are constants, so if I am taking the slopes of ax plus 5, constants stick around unless they're by themselves. Why do I keep using 2? It's frustrating. Constants stick around unless they're by themselves. If I look at the slopes of 3x squared plus b, it would be 6x plus 0. I'm going to say 0 because, like, the slope of b as a constant by itself is 0. Now we have two equations. We have our, are we continuous at x equals 2? And are we connected smoothly at x equals 2? I'm showing all the work that you need to show in case you were doing this on like a free response. But plugging in 2 for x, 2 for x approaches 2. So this is 2a plus 5 equals 12 plus b. This is a equals 12. Great. So I already have this a. So 24 plus 5 equals 12 plus b. 29 minus 12 was 17. Yeah, I'm gonna like graph this because I really enjoyed graphing this on the lesson. We start with ax plus 5 for x's less than 2. I got to do this for the beginning. And then we have 3x squared plus b for x is bigger than or equal to 2. We found that if, yeah, we need these two pieces to connect. Okay, well, if A is 12, kind of shift this line. If B is 17, I shift this line so that they connect smoothly. It's beautiful. It's really nice seeing that. Really nice seeing. All right, same thing here. X is -1. Pay attention to that. X is -1. -1 is the important value. -1. So plugging in -1, I have A minus 3. Plugging in -1, I have B plus 2. Then over here, showing the slopes equaling each other. I got -2A equals -2. There's nothing to plug in here. And I get A is equal to 1. If A is equal to 1, B has to equal -4. AX squared minus 3 for X is less than -1. Cool. So it looks like that. And then we got, well, let's change A to B. Cool. And then we got B minus 2x. For X is greater than -1. Cool. So I got to shift it down. And I got to like rotate them so that they meet up nicely. So if A is 1, that's a nice rotation. If B is -4, look at that. We connect so nicely right there. It's beautiful. Gosh, it's so beautiful. It's nice to be able to visualize. I've never really visualized this stuff in the past. All right, the last two pages are these derivative rules problems. So they're not, they're new. They're new. They're challenging you on your rules and notation. So it's like important to be able to correctly write a notational derivative. The slopes of k will equal the slopes of g plus the slopes of f. Now we will go into our table to find all of our values at pi. We'd say the slopes of k at pi equal the slopes of g at pi plus the slope of f at pi. So here we go. We're going to come up here and look at these two values. The slope of f at pi is -1. The slope of g at pi is -4. So my answer is -5. Great. Now, constants stick around, even in notation. So the slope of 3f is 3f prime. The slope of g over 4 can be written as 1/4 times g. The slope of 1/4 times g is 1/4 times the slope of g. If I plug in 2, great. I got 3 times the slope of f at 2 plus 1/4 times the slope of g at 2. Slope of f at 2 is -2. Slope of g 2 is -1. So I have -6 minus 1/4, so that's -25/4. But be careful. Derivative rules still apply. You must use the product rule if you see a product of x's times x's. You must use the quotient rule if you see a quotient. Don't forget that constants stick around You can either bake it into the 2 and the g and write it as 2g, or you can just leave it out and say, stick around, 2 will be back for you. If you're going to leave it out, leave it all the way out. What do I mean by leave it all the way out? Write it as 2 times slopes of the first times the second plus the slopes of the second times the first. Cool? If you're going to bake it in, bake it in. What we don't want is to do both at the same time, like kind of bake it in halfway, but not all the way. What do I mean by bake it in? I mean like attach the 2 to the g and say you have 2g prime as the slopes of the first times f plus the slopes of f times 2g. Okay, so I prefer to leave out in some cases and bake in other cases. Questions? Jason? Did you get them?
I think so. I got it better than the first time I had to try these.
I think so too. You were always able to do this.
I know you did. You did it.
No, it's just right. Wait, no, is that a 9 or is that an 8?
Yeah.
What is what?
Is this a 9?
It's a 9.
Okay, because you got that. Yeah, dude. All right, so whichever way we do it, just do it correctly. What are we talking about? 2? I have the table over here. G prime of 2 is -1. I hate going back and forth. F of 2 is 4. F prime of 2 is -2. G of 2 is 3. So 2 times -4 plus -6 is -20. If you did here, you would see that 2 would be distributed out. This is a good one because it's notationally might be confusing. We might think of it as a constant. It's not. X times g of x. It needs to be use the product rule. So slopes of the first times the second plus the slopes of the second times the first. And if we plug in 3, g of 3, g prime of 3 times 3. So g of 3 is 4. G prime of 3 is -2 times 3. So that's -6 plus 4, which is -2. Quotient rule for Q. Slopes of the top times the bottom minus the slopes of the bottom times the top. All over the bottom squared. And we're looking at 4. I'm just going to go ahead and plug in 4 and find g prime of 4, which is -3. F of 4 is 3. F prime of 4 is -4. G of 4 is 2. F of 4 is 3 squared, which is 9. So I have -9 plus 8 over 9, which is -1/9.
A horizontal tangent means you set the axis equal to 0.
Slope equals 0. Right? A horizontal tangent is a tangent slope that equals 0. So your m's equals 0.
Okay.
What about this one is a good one because, gosh, you could either bake in the 2 and to be part of the bottom, or you could do the whole leave out, rewrite. Like, let's just keep that constant out, leave it out. Constants stick around unless they're by themselves. Slope of the top times the bottom minus the slope of the bottom times the top, all over the bottom squared. All times a half. Let's plug in the value 2. So I'll have this 1/2. I'll have 2 times 2 because this 2 is get plugged in. I have f of 2 is 4. F prime of 2 is -2 times 2 squared over f of 2 is 4 squared, which is 16. So you probably can't see this. Now you can see it. I got 1/2 of 16 plus 8 over 16. 16 plus 8 is 24. I can simplify however I'd like. Divide the top and bottom by 2. Divide this by 4. It's 3/4. Great. And then what if we had graphs? Well, this is just important to know that, like, if you have line segments, slope of line segments can be found. So if I ask you for m prime at 3.25, well, remember constants sticks around. I probably write this as 1/2 f. I would say it's 1/2 f's slope at 3.25 plus g's slope at 3.25. I kind of skipped a step without the x's. But like, where's 3.25? 1, 2, 3.25. Okay, well, what am I going to do? Well, I can find the slope of f and the slope of g. The slope of f is just the slope of that line segment. Rise over run, up 2 over 1. So the slope of f is 2. The slope of g, down 3 over 1. The slope of g is down 3. And we get -2. Well,
So if I have 32 squared over 16,
32 squared over 16 gets
what do I do?
What did you do is the question.
You could write it as 16 times 2 squared, which is 16 squared times 2 squared. And then all of a sudden the 16 squared over the 16 cancels to just be 1/16. So that works. I feel like that's not probably what I did, though. If you want to check out what I did. Just as like a, oh, okay. You know, I think it would be good just to see maybe a different approach.
May I ask a question?
What are you doing?
what's your video?
No. Let me cook.
I'm doing the homily tomorrow.
Yeah, so you're talking about the new year? Yeah,
Yeah.
Lashana Tova, guys.
You're coming over for dinner on Monday, right?
No, I'm not.
Not you, Master.
Uh,
With your family, not just you. I think so.
F prime of -2 is the slope of f at -2. That slope is -1. G prime of -2 is the slope. Oh, that's 0. That's nice. So I
Is
get
this going in your video?
guys, this one
Yes.
blows.
Reads commentary too.
Oof, bleep that. Oh, post production. I do not do any post production.
So every
Apparently,
question he's had-
I swore on one of my videos. I don't think it's true.
I don't think that's true.
I don't think
I
that's
think
true.
you swore at us the other day in chapel.
No,
About
I
not
did
in
not.
chapel.
That is
Not
blasphemous.
in chapel. About
Blasphemy.
chapel. You're like,
did
you
I?
need to get your shit together.
Oh my
Just
gosh,
said
that was
it's
on
a
video. It's on video. You did that on purpose. You did that on purpose. I feel like you did. I feel like you did that on purpose. All right, what if I ask you for g of 1? This goes back to understanding, guys. Like, plug in x's into function, get y's. Plug in x's into slope equation, gets m's. So, like, g of 1, look up at g, is the y value of g at 1. Look at the video. Look at the video.
No, I did it. I just went too far in. Also, if I do one of them and I know how to do them, can I just not?
Just do 2 of them instead of 5 of them, okay? But yes, do like the middle one.
Your eyes are so blue.
Thanks, appreciate it. Look at that. Must be the light hitting it. Y value 4, slope 1. Y value of g is 4. Slope of f is 0. Ooh, cool. Slope of g at 1 is 1. F value at 1 is -1. Okay, go look up at y values, look at m's, and you enter. Okay, it's another product. Use the product rule. We are almost done. I honestly did not want to record this video again, but I changed the homework from last year, and I'm like, I have to. And I think I made a lot of mistakes on this homework video last year. Okay, f of -3 is the y value of f on -3. Look at your chart. Look at -3. F's y value is 1. F is the lower guy. F's slope at -3 is -1 times the -3 gives us 1 plus 3, which is 4. This is a good example of, leave out constants. I'm going to just put G and F. Pretend it's G of X and F of X. But, like, you don't have to. Leaving out constants, helpful. Slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. 1. The slope of G at 1 is +1. This is not, I wish I had better slopes. F's value at 1 was -1. F's slope at 1 is 0. So that's just going to be 0. I have to find G's value. And F's value is -1 squared, which is 1. So this is going to be -3F's. And you could pull out the 2 if you wanted to, but let's bake in the 2. Let's say slopes of the top times the bottom minus the slopes of the bottom piece times the top over the bottom squared. And we realize that it is not that bad. Later, if we plug in 4, G of 4 is this y value of G at 4. 1, 2, 3, 4. -1. -1. G slope, -3. 2 times 4, 8. G's value at 4 is -1 squared, which is 1. So I got -2 plus 24, which is 22. Well, bam. Peace.